So we're gonna do what we're gonna do today is basically finish the discussion of covariance matrices and then talk about multivariate normal distributions. We'll be a little bit fast, but we're gonna try to cover all the prerequisites. So then next time would be regression mostly. So to remind you, we had discussed the idea of a covariance matrix. So you have a random vector. Let's say you have coordinates y1 up to yn, in this case y1 up to y3. And then what you have is this matrix called the covariance matrix, which has diagonal entries, the variances of y1 up to y3, and then the off-diagonal entries are the pairwise covariances. So you have, let's say, the 1, 2 coordinate would be the covariance of y1 and y2, and so on. And if you note, for example, this entry and this entry, because the covariance is a symmetric operator, covariance of y1, y2 is the same as y2, y1, so these two are going to be the same. Same goes, for example, for these two, and also the other two off-diagonal elements. So there's this mirror image, basically. So you can verify that the first property of a covariance matrix is that it's symmetric. Okay, which means that the off-diagonal entries, the ij is the same as the ji entry, or sigma is equal to sigma transpose. The other thing that is easy to note is if the yi to yn are uncorrelated, which means that the pairwise covariances are 0, then this covariance matrix is going to be diagonal. So all these entries here would be 0. Right? That is what it means for them to be pairwise uncorrelated. And so sigma would be diagonal. The special case is the case where this is true and all coordinates have the same variance, or equal variance case, in which case everything on the diagonal will be sigma squared as well. So this will be sigma squared, sigma squared, sigma squared, and the rest is 0 here. So what happens is I can factor out 1 sigma squared, and then I get I0. So 1, 0, 0, 0, 1, 1. So basically an identity matrix of dimension 3. So in general, you would get sigma squared identity matrix of dimension n by n. So why this matters to us, as you'll see, the assumption that often is made in regression is that the covariance of the noise vector is of this form, sigma squared I, which then means that the coordinates are uncorrelated and the diagonal entries are all equal to sigma squared. Okay, so it's a compact way of encoding this information. Any questions so far? Okay, good. Now the last piece is a little bit less obvious. It tells you what happens if I try to scale by constant and add a constant. So here alpha is scalar, which means it's just a number and it's deterministic, and b here would be deterministic vector. Okay, so I scale y is our random vector. I scale it by alpha and then add a shift, constant shift b. And so this new vector is going to be another random vector. Let's say it could be z. And so it has a covariance matrix, and the question is that what is the relationship between the covariance of z and the covariance of y? Okay. And this identity tells you that what happens is that you can just drop b. So b is not important, or just doesn't change the covariance matrix, and then alpha just comes out alpha squared. So you basically multiply the covariance matrix by alpha squared. And the easiest way to see this is to recall that the covariance of z, let's say, would be expectation of z tilde transpose, where z tilde be kind of our notation for this, z minus the expectation of z, the centered version of z. That's kind of what we did last time, or this is the basic definition of covariance matrix. And so when I add the B, so if you look at Z and then the expectation of Z, the B comes out of the expectation and it gets canceled out. So this really would be alpha Y minus the expectation of Y. So once you do that calculation, we'll do a little bit more of this next slide. And then you plug it in, you would see that the squares comes out. So do it as an exercise, it's a consequence of linearity of expectation. So expectation of Z is really alpha expectation of Y plus B. Okay. So the fact that the covariance matrix depends on the centered version of the random vector is just immediately tells you that this shift is not going to matter. So centering removes any constant shift. The scale, however, is what matters. Now, there is an alternative matrix. So covariance matrix is a shift invariant, but not scale invariant. So shift invariant, but not scale invariant. Anyone knows like a very related matrix, which is shift invariant as well as scale invariant? How do we make it scale invariant as well? Remember, we had the covariance of two random variables, and then there was like associated quantity which was invariant to scaling. Ends with a coefficient, like something coefficients. Yes. Correlation matrix. Yes. So there's an alternate, like there's a companion correlation matrix, which would be just the same matrix on the diagonal, just have one, because the correlation of everything with itself is one. And then the off diagonals would be correlation of y1 and y2, rather than the covariance. And so the correlation matrix, and then you can show that it also is in addition to being shift invariant, it's a scale invariant, because correlation is scale invariant. Anyways, that's on the side. Questions about? Exercise, think about correlation. Think about correlation matrix. You can define it similar to the covariance matrix, but I'll leave it to you to figure out. So the next property is very important for us. So like it's an extension, basically multivariate extension of this. So rather than scaling y by a constant, I can scale it by a matrix, or rather operate on it by a matrix. So we have a matrix A, let's say m by n, right? Usual m by n case. I might write it like this. So it's like a flat matrix. And then n by 1, that's y. So we get ay, which is the another matrix, sorry, another vector, random vector. And it has a covariance matrix, and you can ask what is the covariance matrix of this random vector, and does it have any relation to the covariance matrix of y? And the formula that we have is this nice formula. Covariance of ay is a covariance of y times a transpose. So the covariance of y is just sigma here. And so that's kind of our notation. Let's let the covariance of y be sigma. Then the covariance of ay is a sigma y a transpose. So here it's a little bit more complicated than the expectation. So the expectation, if you recall, anyone remembers what the expectation of ay was? Yes. The expectation of ay, no, because y is random. So
a in the expectation.
yeah, a times the expectation of y. So here we have a comes out on one side and a transpose on the other side. It's a little bit more complicated. So proof, how do we prove this? We define u to be ay, okay. Then I can write covariance of u, that's what I want to look at. And I'm gonna use that notation that I had, u tilde transpose, and I take the expectation. Okay, and then u tilde is just u minus the expectation, and Okay. First step is to simplify this u minus the expectation of u, which we already have all the ingredients. Anyone wants to help me write down a nice expression for this quantity? U is ay minus a, okay, you can call it mu if you like. Let's call the expectation of y mu. So then it would be mu. Then what? What is the next simplification? Extract, okay, yes. Factor this out. Okay, next. What's your name, by the way? Henry, okay. Can you do the next step? So, right, I'm just gonna call this y tilde. Remember, this is the centered version. So it's like y minus the expectation of y, like the centered version of y. So then we're gonna plug this in. I get expectation, u tilde is gonna be ay, sorry, ay tilde. This is the nice kind of thing that we just discovered. And then ay tilde transpose. Okay. Then what? Yeah.
Oh, for the AY transpose, you can switch it to Y tilde transpose, A transpose.
Great. So you could do y tilde transpose, A transpose. And so I get expectation of a y tilde and then y tilde transpose, A transpose. Because if you have two matrices A, B, and if you transpose, you get the products of the transposes, but the order is switched. So this is what transpose does. AB transpose is B transpose, A transpose. Okay, so we applied that. So what will be the next step?
The expectation into the round.
Right, I want to just do a little bit more steps because so we have parentheses around this. So I want to maybe make sure you understand that matrix multiplication is what is the term? That the parentheses don't matter. What is this property? I forgot the name. Sorry? It's not commutative. It's like exactly non-commutative. So commutative means I can change the order. The property that I want, yes. Associative, yes. So it means that I don't, it doesn't matter in what order I do the matrix multiplication. So let's say if I have A times BC, I can remove the parentheses, or I can do AB times C, which then means that it doesn't matter. I can just write ABC. The parentheses don't matter because this is not ambiguous. Whether I do AB first, then multiply by C is not different than if I do A times BC. So by the way, what was your name? Kelly. Okay. So you're a mathematician, I guess, because the only mathematician would know that this property is associative. I think it's correct. Associative. So matrix multiplication is associative, but not commutative. Regular product is both, like scalars is associated, and 2 times 3 times 4 doesn't matter in which order you multiply. The same for matrices. So I'm going to just drop the parentheses. And then I'm going to just reintroduce them around this so that it's a little bit more obvious what we do. So I'm going to introduce it in the middle. So it doesn't matter where I introduce. So I first calculate y tilde transpose. That's a matrix, and then multiply. I mean, you can also introduce other ones here if you want, but that I'm not going to do. So if you recall in the early lecture, I had like BAC, and I didn't put parentheses exactly for that reason. But this becomes clear. So this matrix in the middle is random now. A and A transpose are not random. Now I can move expectation past the linear transformations. So what do I get? And we'll push expectation inside. This is a lemma that we had, if you remember. Y tilde transpose is just a matrix, like that matrix in the middle, and then A transpose comes out to the other side. So we had this idea that, like, you remember, expectation of B, A, C, something like this, is B expectation of A, C, where this was random. The other were not random. This was the lemma that we had. Previous lecture, this is exactly an application of that lemma. Right. Everyone happy with this? So what is the next step? Yes.
The middle equal to a covariance of
The which
like the expectation of y to the middle of y to the transpose is equal to the covariance of y.
yes, this is the covariance of y. This is basically, you just recognize this as the covariance of y by definition. So you're done. We proved that the covariance of u, which is ay, is a covariance of y a transpose. Okay. So it's using a bunch of results, mostly like how to deal with the matrix products, but then also linearity of expectation. This is an application here. Replacing this with the AU is like a linearity of expectation. And this step again is linearity of expectation. Okay, moving to the text. Past the linear operators is, so two applications of linearity expectation. The rest is like properties of matrix multiplication and definition of covariance. Sounds good? Questions? So this identity you're going to use again and again and again until you remember forever. Yeah. Any questions? So covariance of AY is like a covariance of Y. A transpose. That would have been a little bit better. Okay, let's do an example. Okay, by the way, here's the preview of where we use it. So in regression, if you've seen regression, there is a regression coefficient beta hat. You have X transpose X inverse X transpose Y. So this whole thing is like a deterministic matrix. We frequent this statistics, so it's like a matrix times Y. And if I know the distribution of Y, the observations, then like let's say if I know the covariance, for example, matrix of Y, then this formula allows me to calculate the covariance matrix of beta, which is then very useful to set confidence intervals and stuff like that. So we'll see that. So let's do like a concrete example. So I have x1 and x2, both of variance 1, and then the covariance is between the coordinates is rho. I put them into a vector. X is x1, x2. Covariance matrix would be 1 rho, rho 1 by definition. And then I look at this vector, mu vector z. The first coordinate x1 plus x2. The second is x1 minus x2. And it's not hard to see that you can write it as this matrix 1, 1, 1 minus 1 times x1, x2. Okay. Like simple matrix product. And then if I want to calculate the covariance of z, what I end up having is A covariance of X, A transpose, 1, 1, 1 minus 1. Then the middle term is 1 rho, rho 1. And then you get the transpose of A, which happens to be the same as itself because it's a symmetric matrix. So you get this nice formula or just a nice result. And then the rest is matrix multiplication. Anyone wants to help me do the multiplication? Or how would you multiply this out? Yeah.
Yeah, first start with the first A and covariance. So in that case, I first do the products of the rows and the first row and the first two column 1 and column 2. Column 1 would be 1 plus P, and other will be put P plus 1, but they're both the same. and the other one would be like, so row one, column two, plus one. So they're both the same. They both three plus one plus P. And the second one can, the second row will be written as like one minus
Yes, row actually, yes. But yeah,
P minus.
yeah, row minus one. Yes. Okay.
And then
This will do.
and then it's the P.
Right. Which will be
2 plus 2 plus 2B.
2 plus 2 row, which I'm going to write as 2 times 1 plus row.
0 on the second row.
Yes, so this would be 0.
0.
Yes, the other one you don't need to calculate because it has to be the same, but you can do it for
Plus 1.
checking. The last one will be
2 times 1 times.
yeah, 2 times 1. Okay. So there you go. So if you can check our the example that we did early on in the previous lecture, we calculated the variance of this and the covariance of the two coordinates, basically z1 and z2, using bilinearity of the covariance directly. And we got this 0 here as well as this. And this calculation confirms it and also gives this variance for free. Okay, so if you want to compute all the covariances and variances, this approach is really helpful because it gives you the entire matrix. If you just need one of these coordinates, I would say just the bilinearity would be helpful. So I just wanted to calculate the correlation or the covariance of these two. Like let's say if you just wanted to calculate this, this is like an overkill. You just basically need one entry of this and you can just distribute using bilinearity. But if I want everything, maybe this is more natural. Okay. Whichever you prefer. But this approach shines when you want to do like abstract calculation. If you want to deal with abstract quantities and simplify abstractly, let's say A times maybe A inverse or something happens, like you cancel out, this is really useful rather than trying to do numerically. So any questions? And this confirms again that these two are uncorrelated. The coordinates are uncorrelated, despite the original vectors having a potentially non-zero variance. And the last thing I want to talk about in terms of covariance matrices, more or less the last thing, the real last thing I'm not going to spend too much time on, but this is the final property is that a covariance matrix is always positive semi-definite. And I hope you went to the discussion section and hope that the TA has talked about the PSD matrices. Right, okay. How many people now know what a positive semi-definite matrix is? Okay. Anyone can remind us what a positive semi-definite matrix is? Yes. Go ahead.
The inner product of a vector x and
I'm going to use A.
x is greater than or equal to 0.
Let's say matrix is sigma, the vector is A. Can you say that again?
Oh, then A transpose sigma A is greater than or equal to 0.
Right. So let's say sigma is our covariance matrix n by n. A is in Rn. It's a property of symmetric matrices, of which sigma is 1. And then you form A transpose sigma A for a generic vector A, and this has to be non-negative for all basically A in Rn. Okay, that's the property. It is like being non-negative for scalars, but for matrices. Is more sophisticated than, for example, having coordinate-wise non-negative entries. So it doesn't mean that all the entries are non-negative. I emphasize this. So a positive semi-definite matrix can have negative entries. What it means is this quantity is non-negative. So if you form A transpose sigma A, this is always non-negative. And actually, statistics gives you a very nice interpretation of this quantity, as we'll see. Why we care about this, and why it's not negative for a covariance matrix, we're just going to see. So proof of this fact, covariance matrix is always non-positive semi-definite. Let's say I have y. Y is a random vector in Rn. So sigma is its covariance matrix. And I want to form A transpose sigma A, and I want to verify that this is always non-negative. A is some generic vector in Rn. So this is A transpose cov YA. So is there an alternative expression for this quantity that we may just see?
Expectation of why? But you mean the whole thing, or that's the sentence?
The whole thing. The whole thing. It has a simpler. Yes.
For the all A, is that saying all like symmetric A, or is it like any matrix?
A is just a vector.
So it could be any kind.
Yeah, any vector. It's not a matrix, so it's not symmetry doesn't matter. But sigma is a fixed covariance matrix, and A is any vector. Yes. Covariance of A transpose Y. Very close. Why is that covariance of A transpose Y? Because we just apply this result with capital A being A transpose. A transpose is a valid matrix. It happens to be a row vector, but it's also a matrix. So if I apply this result with A, capital A being A transpose, here and then A here. Right? Sounds good. So we got the A transpose cov YA. So what is next? What is A transpose Y or covariance matrix of A transpose Y? What is the dimension of A transpose Y?
The dot product.
Dot product. Okay, so A transpose Y is really A1 up to AN. Y, Y1 up to YN. A transpose Y. So this is a dot product or just a linear combination of the elements. So it's, in particular, it's a scalar. So what is the covariance matrix of a scalar? It's not zero. It's like a 1 by 1 matrix. Has one entry. What is that entry? If you have a 1 by 1 covariance matrix. Yes. Just the variance of A transpose Y. And what do we know about the variance? It's always non-negative. Yeah, variance is non-negative. So this statement that sigma is positive semi-definite really is equivalent to saying that the variance of any linear combination of elements of the random vector is non-negative, which is always true. Okay. So the fact that the variance of a linear combination of the elements of the random vector is non-negative is equivalent to the sigma, capital Sigma, like sigma being positive semi-definite. And you can also see why the rationale behind this quantity, A transpose sigma A, is really, if you want to think statistically, it's really a variance. And in particular, any like positive semi-definite matrix is in fact the covariance, can be the covariance of a random variable. And so it makes sense to look at these. So these are variances of linear combination elements of random. Okay. Gives a very nice interpretation of positive semi-definiteness from a probabilistic perspective. Right. Questions? Does it make sense? Okay. So a particular consequence of this, for example, is that all the eigenvalues of covariance matrix are non-negative. That's a property of positive semi-definite matrices, but some could be zero. And if that happens, if you understand like a little bit, it means that there is a linear combination whose variance, like linear combination elements of Y whose variance is zero, and variance zero has a special meaning. I'll let you think about it. And so it will be a pathological case. So it will be a pathological distribution. Oftentimes this doesn't happen. And so we're not going to focus on it. Read that part for yourself. But in the non-pathological case, all the eigenvalues will be positive, in which case the matrix will be positive definite, which means that this inequality is actually strictly positive for all A. This is typical case. The case where there exists a vector A such that that variance is zero is a pathological degenerate case. Okay, let's move on. So all the eigenvalues of covariance matrices are non-negative. It's a consequence of this fact. This one you can prove. Anyone knows how to prove this? Just for positive symbol. Did you do it in the discussion section? If I have a positive semi-definite matrix whose definition is given somewhere here, it's not obvious. So the definition of a positive semi-definite matrix has nothing to do a priori with eigenvalues, but it's a fact of life that all the eigenvalues are none. Is there anyone that has seen a proof of this? No. Okay. Proof. As an exercise, use eigenvalue decomposition. Eigenvalue decomposition exists for any symmetric matrix, and an application here would immediately give you that the eigenvalues are non-negative. So you start from the definition, and using that definition and the eigenvalue decomposition, you should get this fact. Okay, there's one more topic here, which I'm going to skip mostly, and that's the correlation. So using that fact, the covariance of AY is A of Y. A transpose, we can construct an A such that this side is identity. And that part, there are many choices. In particular, choice of interest is sigma -1/2, or the inverse of the square root of sigma, which I hope that he has talked about, that there is a square root for any positive semi-definite matrix. There's a symmetric square root, and you can invert it. If you can invert it, then a little calculation using this fact shows that the covariance of the result is identical. So there is this linear transformation that we can do to Y10 or decorrelate the vector. So it's related linearly to the original vector, but the covariance matrix identity. This is useful for us later at some point in the course, but it's not used as often. So I'm gonna just mention it. Yes.
Yeah, so that's a division sign. That's
Which one?
you're dividing by the identity. So yeah, I understand.
Oh, here now, this is just I'm saying we want this to be equal to the identity.
Oh,
Yes. Yeah, you wouldn't write division from matrix.
yeah.
Yeah, it's just we set this side to identity. I'm just what is A such that that happens. There are multiple A's, not all of which symmetric. here's another example, which is not symmetric if you do the eigenvalue decomposition, but to define the sigma 1/2 or negative 1/2, you can use the eigenvalue decomposition. And yeah, now I'm going to stop talking about this because it's going to take a while, and I'll let you decide, or whether you want to learn it now or at some other point. That's done. Okay, so any questions about the probability review / extension to random vectors and matrices and covariance matrices, stuff like that? Any questions about any of that? So we did the expectation of a random vector, we did the covariance matrix of a random vector, and understood how they transform under linear transformations. The last piece that we need is the normal distribution or the Gaussian distribution, which I'm hoping that at least in 1D, everyone has seen, right? How many people know what the normal distribution is? Okay, how many people know what a multivariate normal distribution is? Okay, good. So what is a normal distribution? Let's say n equal to 1. So suppose you have x, you have a random variable, right? And a random variable is completely specified by its distribution. And we're working with a continuous random variable here, which we say that it has normal distribution by writing this. So x, this tilde, which is the notation for has distribution, normal with mean mu and variance sigma squared. So it's a 2-parameter distribution. So it has 2 parameters, mean and variance. What does it mean to have a normal distribution? Yes.
Yeah, it's symmetrical around the bus parameter.
Yes. So a little bit more precisely, it means that it has this particular density. Okay. And a feature of that density is if I plot it as a function of x, it would be centered and symmetric around mu. It has this bell shape, and the variance gives you this spread. Okay, so the shape is not characteristic of the Gaussian distribution. Any unimodal, sufficiently smooth, continuous like distribution would have this form. The fact that the tails go down like exponentially and like a square exponential. So as you go, as x becomes large, the tail behaves like e to the negative x squared divided by something. Okay, this is very fast decay. E to the negative x squared decays very fast. So if you move away from the mean, basically, x minus mu. If x minus mu becomes, the absolute value becomes a little bit large, let's say bigger than twice the variance, then it's like this is going to be twice or 3 times the variance or 4 times the variance. This is very small. So the probability that you like find a random variable around there is very small. Okay, that's the characteristic of the normal. The tails decay like super exponential. Okay, this is the key property. The tails is what defines that normal. The fact that it's symmetric, many distributions are symmetric. Like a T could be symmetric, but has a fatter tail. Okay, it looks like this if you plot it, but tails are like polynomially decaying rather than quadratic exponential. So the kind of the tails really characterize. Right. Like the fast decay. What the tails characterize this distribution compared to the competitors. Okay, and then you can see how like they appear. So the mu is like the actually ends up being the mean, like the expectation, and the sigma squared happens to be the variance. So I think this died. Give me a sec. So sigma squared happens to be the actual variance. So these parameters are exactly the mean and the variance. The multivariate normal distribution has the same property. Sorry, it's like the extension of this univariate like distribution to a multivariate case. So you have a vector y1 up to yn, and we write it like this. So it has distribution normal with mean mu and now a covariance matrix sigma. So it has two parameters: mean vector, right? Mean vector, and a covariance matrix, which kind of replaces mu and sigma squared in the univariate case. And it's characterized or defined by the density. So the density is now a multivariate, a function of multiple variables. So function of y1 up to yn. So that's the density of a vector. And it's just the density is given by this quantity. And the characteristic again is that the tails, which are a little bit more complicated in this case, decay like a quadratic. This is a general quadratic. It's like here is like a univariate quadratic. This is a multivariate quadratic. So in all directions, kind of decay away from the mean. Okay, I'm going to show you a picture, but that's the key part. This part is just to normalize so that this integrates to 1. And this quantity here is just the determinant of sigma. Okay, and the rest is kind of normalizing fact. So the key part is the e to the negative of this quadratic, which tells you like how fast it decays away from the mean. And again, this mu would be happens to be really the expectation of y would be mu, and then the covariance matrix of y really would be sigma. So they have the same meaning. So in fact, mu would be the mean, and the covariance would be sigma. This you have to prove for yourself. I mean, given this density, these facts are going to pop out. And in particular, sigma is PSD. And here we're going to assuming to be invertible. So you can see the inverse of it happens like here's and there. And if you look at the one-dimensional case, it recovers the formula that we have in the 1D case. Okay. And if you have seen bivariate normal, if you write sigma in a particular fashion, if you write sigma as like sigma 1 squared, sigma 1, sigma 2, and then rho, which is correlation coefficient, sigma 1, sigma 2, rho, sigma 2 squared, and then invert it, replace this inverse with that inverse, you get the formula that people write down to the bivariate normal. So this just encompasses all the things that we've seen about them. And it's, I would argue it's nicer. So this is a general quadratic form. Quadratic form in Y. Okay, so what it looks like is if I look at the contours, so y1, y2, such that the density is equal to a constant, which happens to be also the same as saying all the y1 and y2, such that this quadratic form is some other constant that you can verify for yourself. This is basically a quantity which is one-dimensional. So this is 1 by n by n by 1. So this like multiplies to a scalar value. So this Fy is equal to C if this quantity is equal to C prime for some other C prime related to C. And so I can plot these, and these would look like ellipsoid. Let's say I'm doing it in R2, they would look like these would be the contours of the distribution. What it means is that on one of these, let's say on this circle here, this is the case where you have zero correlation. F of y is the same. So all the y's have the same density. So they're equally probable. And the kind of shade tells you like the strength. So this is a larger value. So this, for example, could be, I don't know, 0.1 here, this could be like, f of y could be 0.001 or something like that. So everything on this circle is equally probable, but is much less probable than Fy. So if you sample, most of the time you find things near the center and less outside. Then you have a non-zero correlation, let's say correlation 0.7 here, the contours would be ellipsoid. you can see. And then these are more informative in the sense, if I know, for example, that y1 is 1 here, then I can kind of read off the conditional distribution. Things would be mostly in this area. So they're gonna center here around that and then spread out. But if I see, for example, something here, -1, then things would be in this interval mostly. You can see from the contour because the probability is higher there and it's center near here. So most of the things, if I know y1 is 1, most often y2 would be around this point. If I know y1 is 1, it's most likely would be here. Okay, so the correlation tells you something about, like, if I know one, I know more information about the other. This one, in this case, the correlation is 0, kind of there. We'll see in this case, in the normal case, it means they're independent actually. So if I know it's 1 versus, let's say, -1, it doesn't matter. So the location of, mostly they're going to be found in the here, as well as if I know it's 0 or any other one. It may look like the intervals are different because of the shade, but for conditional distribution, you have to normalize. Once you normalize, the conditional distribution will be exactly the same. So it doesn't matter if I know y, the conditional distribution of y1 given y2 given y1 is the same. It's exactly going to be normal, standard normal. So no information if I know y. There's y1, there's no information about y2, but here if I know y1, there's plenty of information, especially if y2 happens to be kind of way out here. It's very unlikely, for example, that y2 would be here. Y2 would be very close to the center of this distribution here. Anyways, this is the interpretation. So you can interpret how this tilts, and this tells you about the correlation and the conditional distribution, stuff like that. Sounds good? Yes.
Are you only able to tell the conditional distribution that I guess has some density, like it's like has some color or density? So what if you did something like y1 equals 2? Will there be no additional density because there's no
y1 equal to 2? Yes, there is. So this just spreads all the way to infinity. I'm just not showing. So the support is all the way to infinity. Yes, it still works. Like this is very unlikely. For example, y1 being equal to 2 is very unlikely. But I think here we're doing like correlation 0.1, but the variances are 1. So if you know a single normal distribution being bigger than 2 is like very unlikely. Like probability is less than you calculate, but whether it's bigger than 2 or -2, it's like less than 5%. It's about like the absolute value is bigger than 2. But if you happen to observe something above 2 here, then you can actually figure out what exactly, what is the distribution of y2. Maybe I should give it as an example for you to figure out. There's a slide about conditional distribution of the Gaussian, which I'm going to very briefly mention towards the end, because we're not going to use it, but you can use it to argue what would happen. Okay, here's the 3D picture, which is not giving you very much information because I should probably rotate it. But so the things are going to be in the case where you have correlation bigger than 0, they're like centered around basically there's a ridge. So it's like you would have like the bell would be tilted towards the y1 equal y2 case. And it would be also sharper because like the height would be higher because you'd have this divided by the determinant. Determinant would be less than 1, and so it blows up the density. The density would be sharper, and more mass would be near y1 equal y2. I wish I could tilt it. Try to plot these for yourself using the software or ChatGPT or Cloud, and then you can play with it. Just look at it from different angles. You'd see that this is like mostly around y1 equal y2. The more correlation gets closer to 1 or -1, and otherwise it's just going to be symmetric. So you have to imagine this is a mountain like with a peak at the center. These are just contours, and that's another mountain peak at the center, but it has like a ridge kind of. It's not a ridge, but really it's like a peak, but more spread out in this direction than the other. Questions? So we're not going to unfortunately use this these much. These are very interesting facts. What we're going to use is the consequences of this definition. Everything that I'm going to talk about follow from this definition. The main thing that follows is this property that we're going to use a lot. So linear transformations as well as affine transformations really of multivariate normal random variables are again have multivariate normal distribution. Or we can say that normality is preserved under affine transformation. So what does this mean? It means that if y has a normal distribution with mean vector mu and the covariance sigma, and then I have a matrix A, m by n, let's say, and then B is m by 1 is a vector, and I have this level n here to emphasize that this is a normal distribution Rn. So y is really a vector in Rn. It's a Gaussian random vector or normal random vector in Rn, and I form this quantity a times y plus b. Let's call this u. So this is a general affine transformation. If b was 0, if I did just a times y, that would be a linear transformation. This is an affine transformation. What this result is saying is that this new vector is also going to have a multivariate normal distribution. Okay. So if I do an affine transformation of multivariate normal distribution, the distribution remains in the same family. What changes is the mean vector and the covariance matrix, and we already know how it changes. So the mean of this, the expectation of u, I hope everyone knows by this point. You can use the linearity of expectation. You get a times the expectation of y plus b. Here, the expectation of y would be mu. So I get a mu plus b. This holds in general whether y has distribution normal or not. Doesn't matter. And then if you calculate the covariance matrix of u, it would be cov ay plus b. And if you recall, a constant shift doesn't matter. We discussed this, so I can drop the b. So I get cov ay. And then we use the formula that we just proved, a times cov y times a transpose. Okay, and so this would be a sigma a transpose. So this formula is also always true, no matter what the distribution of the original y is. What this property is saying is that I just know now that if y is normal, then the result is normal. And since I know the mean and the covariance matrix, I know the full distribution perfectly, because the normal distribution is characterized by its mean vector and the covariance matrix. A general distribution is not characterized necessarily. These are second order, first order, and second order properties, but the normal distribution is completely determined by the mean and the covariance matrix. Okay. And because I know it, I just know everything about this distribution. Okay, so the only piece here that's new is this fact that it's normal. Questions? Anyone knows how this is proved? How do you prove this? Yes.
Moment generating.
Okay, that's a very good way of doing it. So you can do moment generating function, which is like the Fourier kind of view of the density. So you do it in the Fourier domain. You can also do it in the original domain. So what I need to do is to compute the density of this new vector and show it that it has this form. And for that, I need kind of like some tools from calculus, or if you've seen it, they call it the change of variable formula. You need a multivariate version of this. I transform one random vector into another by a function. It doesn't have to be linear or affine, it could be nonlinear. And then there's a rule how the density is transformed. Anyone remembers? And I heard something in the right path. There's a keyword. What is the quantity that appears in this change of variable formula? Starts with J. Yes, Jacobian. Yeah. So you write down the Jacobian of this transform and also the inverse of it, and then there's the formula involving the Jacobian. Jacobian transform the volume basically, and it would appear like if you remember the determinant kind of is related to the Jacobian of a linear transform and so on. The determinant of the Jacobian appears in the formula as well as the inverse, and write down, and then everything works out. That's the proof, which I'm not going to do. Sounds good? This is the main property we're going to use. Okay. affine transformations leave the multivariate normal family invariant, so you're staying in the same family. Yeah, again, this is important because beta hat is a linear transformation of y, and if the observation is multivariate normal, then the coefficients of the regression would be multivariate normal. Okay, let's move on to the second property, which is really not an independent property. It's just a consequence of the previous property. So if you just remember that or learn that, that's enough to get this. So marginals of multivariate normal distribution are again multivariate normal. So what do we mean by marginals or marginal distribution? You want to reverse? What is a marginal?
It would be, in this case, it would be the distribution of y1 or y2 holding the other.
Yes, so if you have like just, I mean, okay, this is a little bit confusing because this y1 and y2 are not necessarily scalar in my case. But if it was like a bivariate, let's say y was just having two coordinates, then distribution of y1 would be a marginal. Distribution of y2 would be marginal. More generally, if I have multiple coordinates, what I'm calling a marginal is really, let's say y1, y2, y3, y4. Any combination, like any subset of these that you pick, I could pick in any order or any subset. Let's say I pick y4 and y2. Okay, the distribution of this subset, like this subvector, is a marginal, and the claim is that any basically subvector will have a multivariate normal distribution. Okay, so to see this, let's say I look at this y4 and y2, and the claim is that I can write it as a linear function of y1, y2, y3, y4. See why that's happened. So there's a matrix that if I multiply, I get that. You want to help me? The first is 0. Yes, 0, 0, 0, 1. This is going to get multiplied by that and selects y4. And the second one would be 0, 1, 0, 0. Right? So 2 by 4, if you multiply, you get that. And so this is some a, this is y. This is a linear transformation that previous results tell you that if y is multivariate normal, then this is going to be multivariate normal. So this is going to have multivariate normal distribution. Okay. And you can easily figure out the mean and the covariance matrix. In this case, it's going to be easy because you can use that formula, but you can also just read it. Like the mean of this would be the mean of y4 and then the mean of y2 put together. And then the covariance matrix is just the variances of these two and then the covariance, which happen to also be a submatrix of the original covariance matrix, which you would get if you do the A times covariance matrix of Y A transfer. Anyways, this is just a very simple property, okay? And it doesn't matter in what subset you pick, in what order you pick, that would generate a multivariate norm. So you can generate easily many marginals. The way that I do it here is I'm doing a block partitioning. This is often what you do. You don't kind of mess around with the order. So for example, I have, let's say y, let's say, okay, I'm going to do z because to avoid confusion. Let's say y has, okay, let's do this. Let's y has coordinates z1, z2, z3, z4, z5. And I'm going to split it into two parts. So a 2 by 1 and then a 3 by 1 vector. So I'm going to call this top one y1. This is now a block vector, like, and this is also y2. So y1 would be 2 by 1, y2 would be 3 by 1. That's what I did here. So it's a block partitioning of the vector. And then this can be, like the y1, for example, can be written as, you can verify it's going to be identity 2 and then 0 times y. And the other one would be basically 0 and then identity 3. So proper dimension. So this would be 3 by 5. This would be 2 by 5. And so on. And then you can easily kind of The interesting thing is that what the covariance matrix of these two would be, and it's either way that you can compute it either directly from definition or using that formula A sigma U transpose, it would correspond to a block partitioning of the covariance matrix. So if I partition the covariance matrix like this, 2 by 2 and then 3 by 3, and then there's a cross term which is like 2 by 3. So I partition exactly along the same indices. So the first two elements in the rows and columns correspond to y1, and the rest, the three remaining elements correspond to y2, and then I partition like this. I get this submatrix sigma y11, which is 2 by 2. That would be the covariance matrix of y1. So the covariance matrix of y1 as a vector. Sigma 2 would be the covariance matrix of y2. And this sigma 1 2 is really like a cross covariance matrix, if you want cross covariance matrix. We haven't defined it, but it just comes up naturally. It's just a matrix that has the covariance of pairs of elements from y1 and y2. Okay, so you can just write it down. It would be the covariance of z1 and with z3, z4, and z5. That would be the first row, and then the covariance of z2 with all the other entries of y2 in the second row. Okay, so this block partitioning is very useful for kind of determining the relation of y1 and y2. Is this kind of roughly okay? This is oftentimes what you do. Yes.
Are y1 and y2 defined in terms of like identities? What is that I2 take?
So what I'm doing here is like I'm kind of arguing that you could write y1 as a matrix times y. So this in this case, for example, it would be, what I'm saying is that it's like 1 0 0 1, that's identity 2, and then the rest is 0. So this times y is just compact way of writing things. So this would give me y, actually it's with z. Unfortunately, confusing notation because I'm using y1. So this would be z1, z2. This is really vector y1. Okay, and this is like I2, and this is like 0, 2 by 3 if you want. Okay, 2 by 3, this is 3 by 2. Maybe, yeah. Or actually 3 by 3, sorry. It's 3 by, yeah. Oh no, 3 by 2. Yeah, 3 by 2. Because that's the sum to 5. Okay, so the block partitioning is what I'm trying to do here. The fact that the marginals are multivariate normal is kind of straightforward. Okay. Sounds good. So in particular, there's this interesting consequence. If you do this block partitioning, then the interesting thing happens when this is 0. Okay, this cross covariance is 0, which then means that the pairs, like the two blocks, or the y1 and y2, are uncorrelated. As vectors, they're uncorrelated. We say they're uncorrelated, the cross covariance is 0. So sigma 1 2 is 0 here. The third property is that this is equivalent to y1 and y2 being independent, like random vectors. So why this is significant? Because this relation in general is not true or goes in one direction. So so in general, independence implies uncorrelatedness, but not the other way around. Okay, two random variables that are uncorrelated are not necessarily independent. Two random variables that are independent are necessarily uncorrelated. So independence is strong here. Okay. What this result is saying is that in the normal distribution, they're equivalent. So if you have a random vector with elements that are kind of partitioned, so this random vector as a whole has a normal distribution. In other words, we say that y1 and y2 are jointly normal. It means that if I put them together as a vector, it has a multivariate normal distribution. Then if they're uncorrelated, then they're going to be independent. That's what this property is saying. And oftentimes, like people that start learning about probability just confuse uncorrelated with independence. it's okay to confuse them in the normal, this like family, because they're equivalent. It's not okay to confuse them outside. Independence is a much stronger notion. Have people kind of seen this like idea that uncorrelatedness and independence are different? Okay. So the proof here, I'm not going to do it very carefully, but because I mentioned this in the early, like in the morning session, I'm going to do it here. So the proof goes via that, you can do it via homogeneous functions, or you can do it via the PDF. Okay, so the key is that when I form, if this is y, then I form y minus mu. Let's say for simplicity, mu is 0. That simplifies everything. You can do it when mu is non-zero as well. I'm just going to give you the idea. So if mu is 0, assume for simplicity. So when I write the f of y, it would be something here. It's like a prefactor. I'm going to write it as kind of c prefactor, and then you'd get exponential negative y transpose sigma inverse y. Okay. So sigma inverse would be sigma 1, 1, 0, 0, sigma 2, 2 inverse. And this is a block diagonal matrix, and there's an easy way of writing the inverse. Anyone knows how to invert a block diagonal matrix? I'm just going to invert the diagonals. So you can verify that this is the inverse by just multiplying the two. Sigma 2 inverse. Again, just put the inverse on the diagonal. And so if you do this here and then you do the expansion, you'd get y1. So this would actually be y1 transpose, y2 transpose, sigma 1, 1 inverse, sigma 2, 2 inverse. And then y1, y2, these are blocks. But you can expand, and it ends up being like y transpose, y1 transpose sigma 1 inverse y1 plus y2 transpose sigma 2, 2 inverse y2. Okay, and because exponential kind of factors over summation, so you get c e to the negative. I'm missing a 1/2 here as well. So you get 1/2 y1 transpose sigma 1, 1 inverse y1 times e to the negative 1/2 y2 transpose sigma 2, 2 inverse y2. Not sure it's readable enough, but it factorizes. So it factorizes into a piece which only depends on y1 times a piece that only depends on y2. And this shows that the distributions are independent because after proper scaling, one would be the PDF of y1, the other PDF of y2. And so when you have like an f y1, y2 factorizes into, say, f, then this is like equivalent to independence. So the fact that this sigma inverse happens here, and when you do have zero coordinate cross covariance, the inverse is block diagonal just transforms into this factorizing. So the density factorizes. Sorry for the bad handwriting, but you do it as an exercise. You just write it down, and then density factorizes as a function of y1 and a function of y2, and that implies independence. So what we really showed is that if this is 0, then they're independent. The other way around is kind of always true. It's not something that needs to be shown. Sounds good? Okay. Almost done. So the last piece of information is this, which we're going to talk about briefly at the start of the next lecture. you can also write down conditional distributions of multivariate normal are also multivariate normal. So if I condition, for example, y1 and y2, if I know y2, conditional distribution of y1 given y2 is normal, I just have to specify mean and the covariance matrix, and they're not obvious, but they're formulas for them. And then this allows you to do a lot of interesting things, which we don't do, but if you do even statistics or Gaussian processes or other advanced stuff, this stuff is useful. Okay, so we'll continue next time, talking a little bit about this, and then move on to the issues. Thank you.